morning. Travis Eaglin. I'm doing the results for the comparing experiment, and I'll be the group reporter for group 3. The objective of the experiment was to determine the latent heat of vaporization for using the comparing equation over a range of temperatures and pressures. Our expected outcomes, we needed to verify the data based off the steam tables and the thermodynamics books. Also, we need to determine the enthalpy from acquired measurements in pressure and temperature. So to go back through a little bit of the theory again, the latent heat is defined as heat energy required to change 1 mole of liquid at its boiling point under standard atmospheric pressure. The comparing equation is shown below, and it relates pressure, temperature, specific heats, and specific volumes. You also have your ideal gas equation again under it, which is pretty much the same thing except it uses the gas constant in its formula. A refresher on the apparatus for this experiment. I'm not going to run all the way through them again. We did deviate a little bit in the procedure. The procedure for at number 1 for the flask said to use 200 milliliters. We filled ours up to about 800 milliliters. Also, too, not shown in here, this configuration, there's also another separate flask that's in this little area here that's attached to the vacuum control valve. I do also want to mention here this vacuum control valve is attached to a smaller piece of the pipe here to allow for the vacuum coming from the flow of the pump through the tank. So part of procedure 1, using the data acquired, the data gave us temperature here and pressure. I took that data, we needed to estimate local derivatives to calculate our change of pressure over change of temperature, and to use that to calculate the specific heat, the latent heat of vaporization. And also too, we need to approximate as a function using the ideal gas equation. So using that data, I was able to use the comparing equation and get calculated specific heats. But I wanted to specify or show here is in the steam tables, they do temperature in increments of 5 degrees. So it's 30, 35, 40, so on. So what I ended up doing was with our data, doing an average close to that 30 degrees and so on to compare my tabulated latent heat versus my calculated latent heat. I also do want to mention that temperature started from 29.75 degrees Celsius and ran up to about 99 degrees Celsius. Doing that data, here's my plot from procedure 1. The blue line here is from the steam tables. As you can see, it's a linear straight line. The data obviously didn't come out right. It was pretty comparable up to about 45 degrees Celsius, and then you can see start getting some weird results. So part of procedure 2, I needed to plot the temperature versus pressure from the given results, and then take that and do a linear regression to where I got a formula from that, and it'll get an exponential shown there. Use that exponential to get my temperature versus enthalpy data here. As you can see from the first procedure, my chart was off. As you can see, it gets a little bit closer to what the actual result is in procedure 2. So part of procedure 3 needs to integrate the comparing equation, which use the ideal constant. Here's my calculations. I need to substitute for specific the latent heat, and A plus B T linear formula, and then integrate it to get an LMP equals a constant plus A over RT plus B ln of T over R. Using this equation and the data, there was an Excel parameter you can use. You get this data here, where it ends up solving for your C1, C2, and C3 using the coefficients. Plug that in to get a specific heat, a latent heat vaporization of negative 6.44. So I'll say that is not right. I did get some lower values than what specific lake heats usually are. They're usually in the 2000s range, and a little bit up. As you can see, I'm nowhere close to that. I did discuss that with Philip, and I believe that there is some data error in calculating this. So a few talking points I didn't mention back in the apparatus. We did use boiling beads. The reason why we did use boiling beads is because it helps make the boiling more smoothly. It also ends up creating more nucleation areas to facilitate the boiling. Makes that more easier. Another thing that we did run into, since we changed it to 800 milliliters to 200 milliliters, it took a little longer to get that volume hotter. So we did have a little bit longer time waiting there. Also too, there's another talking point about the thermocouple location. It mentions in the procedure to keep it just below the surface of water, below the surface of the top level of water. The reason why is to avoid any kind of localized heating from being at the bottom by the heat plate, from at the top, and also too along the sides of the flask, from the bottom and the sides of the flask, and also your temperature gradient for the amount of water that you have in there from the bottom to the top. So in conclusion, procedure 1 showed to be very inaccurate as displayed by the graph. Procedure 2, we provided a better estimation for the enthalpy than compared to procedure 1, but still shouldn't be as good as procedure 3. Procedure 3 should have been the better way to be able to estimate your latent heat or your enthalpy, but due to resultant data, it ended up happening that way, but it should be procedure 3 being the better way to do it.